Pluto is a small planet that is hidden and far away, a planet that once had a person, however, a member of our solar system. Recent, alarming statements made by leading astrophysicist Neil deGrasse Tyson and others have brought Pluto back into the spotlight with an astonishing revelation. They suggested that the frosty world is on a course that could impact Neptune. But how could this possibly happen, and what might be the result of such a huge event? Are we witnessing an intriguing peculiarity of the galaxy, or is there something more to this looming, incredible crash? Join us as we investigate the potential outcomes of a previous Neptune-Pluto collision. Pluto, a planet that was reduced to the size of a dwarf planet partly because of its unique orbit, continues to be of interest to the galactic community. Based on recent predictions made by leading researchers, Pluto's orbit is dangerously close to Neptune's. Astrophysicists Neil deGrasse Tyson and Michio Kaku are sounding the alarm about a potentially hazardous crash between these two worlds. But how is such an event even conceivable? Pluto's journey around the Sun is unlike that of any other planet in our solar system. It takes an incredible 248 years to complete one orbit. Since its discovery in 1930, it hasn't even completed one full revolution. But Pluto's orbit is distinguished by its extreme elliptical shape, departing significantly from the nearly circular orbits of the major planets around the Sun. What makes Pluto's orbit even more unique is its inclination, calculated at 17 degrees from the ecliptic plane. Unlike the other planets, Pluto's path is much steeper. This inclination and eccentricity add layers of complexity to its orbital pattern. One of the most fascinating aspects of Pluto's orbit is the point where it intersects with Neptune's route. For approximately 20 years in each orbit, Pluto actually gets closer to the Sun than Neptune. This raises a natural question: why hasn't Pluto crashed into Neptune? The answer lies in the gravitational effects of other planets. When Pluto's orbit was first studied shortly after its discovery, astronomers tried to figure out its unique route compared to other planets whose orbits are relatively close. Pluto's orbit stood out with its steep inclination and elliptical shape. The mystery deepened when astronomers realized that Pluto's orbit does, in fact, cross Neptune's. Despite this, the stabilization of Pluto's orbit in the face of these complexities is an example of space mechanics at work. The three-body problem in space involves figuring out how three objects, like Pluto, Neptune, and the Sun, interact and influence one another through gravity. It's like trying to predict where they will go based on where they start and how they interact. In Pluto's case, this issue demonstrates how its orbit, the gravity of the Sun, and Neptune's influence all work together in a complex way. Terms like scope libration and ASU libration, along with VZK oscillation, are part of this puzzle. According to astrophysicists, what keeps all planets in their orbits is ASU libration. In the case of Neptune and Pluto, this term means that whenever Pluto crosses Neptune's orbit, it is positioned at a crucial 90-degree separation from Neptune. This spatial separation is key to preventing their orbits from intersecting. Scope libration, on the other hand, refers to the vertical movement of a body within its orbit. For Pluto, this means that when it comes closest to Neptune or any other giant planet, it is positioned far above their orbital plane. This adds another layer of protection from potential collisions. Another important factor in this situation is the VZK oscillation, named after three researchers, Kai, Zhao, and others, who studied how objects move in space. It affects the way three celestial bodies, like Pluto, Neptune, and the Sun, pull on one another with their gravity. This gravitational influence determines their movement. For Pluto, the VZK oscillation helps explain why its orbit, despite appearing irregular, remains stable over long periods. Despite the apparent unpredictability of Pluto's path, these orbital mechanisms help maintain its stability, ensuring that it does not crash into Neptune or stray off course. The three-body problem is key to understanding how these orbits change due to the gravitational pulls of celestial bodies. Studying this phenomenon helps scientists learn more about Pluto, the solar system, and distant worlds. Mathematical simulations from the late 1980s revealed that despite its stable properties, Pluto's orbit is actually turbulent. Minor deviations in initial conditions could lead to significant variations over thousands of years. However, despite these fluctuations, Pluto's orbital properties have been found to maintain stability over incredibly long time scales, effectively preventing the current chaos predicted in earlier theories. Computer simulations have helped scientists learn how massive planets like Saturn, Jupiter, and Neptune influence Pluto's orbit. Pluto and Neptune have a unique orbital relationship. Every two orbits of Pluto around the Sun correspond to three orbits of Neptune. This resonance helps keep Pluto's orbit consistent. However, Neptune isn't the only player in this cosmic balancing act. Jupiter's gravity, along with Saturn's, plays a crucial role in maintaining Pluto's stability. These studies demonstrate that Jupiter's gravitational force alone is enough to ensure Pluto follows a consistent course for millions of years. It is as if Neptune, Saturn, and Jupiter are all working together to keep Pluto safely in its path. These orbital mechanisms are essential for maintaining stability and order in space. Without them, the solar system would be much more chaotic. Pluto and other celestial bodies could collide or be ejected from their stable paths, setting off chain reactions with unpredictable consequences. This is why understanding Pluto's orbit is so crucial, especially in discussions about its potential collision with Neptune. Studying Pluto's orbit provides a clearer picture of the dynamic nature of the solar system. Even orbits that seem unstable can achieve equilibrium through complex gravitational interactions. This highlights the importance of continuous observation and research into celestial mechanics. Exploring the universe often forces us to confront its bizarre nature, and Pluto's orbit is a prime example of this unpredictability. The concept of orbital chaos refers to the sensitive dependence of a celestial body's orbit on its initial conditions. In Pluto's case, even slight changes in its speed or position can significantly alter its long-term trajectory. Computer simulations have been immensely helpful in predicting Pluto's movement. By making small adjustments in the simulations, astronomers can observe how minor changes lead to drastically different outcomes over time. Interestingly, despite Pluto's chaotic orbital tendencies, its long-term trajectory remains stable over billions of years. This means that while Pluto's short-term orbit may appear unpredictable, over vast timescales, an underlying order emerges. Predicting celestial events, especially when they involve tumultuous orbits like Pluto's, remains a significant challenge due to inherent uncertainties in orbital mechanics. Although modern mathematical models provide powerful tools for understanding and predicting the paths of celestial bodies, they also highlight the limitations of our predictive capabilities. These models rely heavily on initial conditions. The future of Pluto's orbit and the solar system's stability. Despite Pluto's long-term stability, astronomers remain intrigued by the potential for orbital shifts over millions or even billions of years. The gravitational dance between Neptune, Pluto, and other giant planets suggests that while Pluto is safe for now, small perturbations could lead to significant changes in the distant future. One of the key factors in Pluto's orbital stability is the influence of resonances. As mentioned earlier, Pluto and Neptune are locked in a 3:2 resonance, meaning for every 3 orbits of Neptune around the Sun, Pluto completes 2. This resonance prevents the two planets from ever colliding, as their closest approaches are carefully regulated by gravitational interactions. However, even this seemingly stable relationship is subject to minute variations over time. The role of the outer planets. Jupiter and Saturn also play crucial roles in shaping Pluto's orbit. Their immense gravitational fields exert influence on Neptune, which in turn affects Pluto. In past simulations, astronomers have found that over extreme timescales, interactions between these gas giants could subtly alter Neptune's orbit. If Neptune's orbit were to shift even slightly, it could disrupt Pluto's delicate balance, potentially leading to an altered trajectory. However, the likelihood of a direct Pluto-Neptune collision remains extremely low. The complex interplay of gravitational forces acts as a safeguard, ensuring that their paths remain separate despite their apparent overlap. Could Pluto be ejected from the solar system? Another intriguing possibility that arises from long-term simulations is the potential for Pluto to be ejected from the solar system entirely. If a sufficiently large external force were applied, such as the influence of a passing star or a rogue planet, it could disrupt Pluto's resonance with Neptune and send it into a more erratic orbit. Over millions of years, this could eventually push Pluto into interstellar space. Such an event would not be unprecedented. Scientists believe that our solar system has likely lost numerous small planetary bodies over its lifetime due to gravitational interactions. The same forces that keep Pluto stable now could, under rare circumstances, destabilize it in the future. The broader implications for planetary science. Pluto's complex orbital behavior provides a valuable case study for understanding the broader mechanics of celestial bodies in the solar system and beyond. Many exoplanets, planets orbiting other stars, are found in similarly resonant orbits, suggesting that the principles governing Pluto's stability are not unique to our solar system. Studying Pluto's interactions with Neptune and the other giant planets helps astronomers refine models of planetary formation and evolution. It also enhances our ability to predict the long-term stability of other celestial bodies, including potentially habitable exoplanets in distant star systems. Conclusion: the mystery of Pluto continues. Pluto's orbit is a fascinating example of how celestial mechanics, gravitational resonances, and long-term stability work together in the cosmic ballet of the solar system. Despite its eccentric path and apparent instability, it has remained in a stable yet dynamic relationship with Neptune for billions of years. While discussions about a potential Pluto-Neptune collision spark curiosity, current models suggest that such an event is highly improbable. Instead, Pluto will likely continue its intricate dance with Neptune and the other outer planets for millions, if not billions, of years to come. However, the universe is ever-changing. With new advancements in computational simulations and space observation, our understanding of Pluto and the outer solar system will continue to evolve. As we unlock more of the secrets hidden in the depths of space, Pluto remains a key player in the ongoing exploration of our cosmic neighborhood. Concerns regarding a potential effect, despite everything, exist between Neptune and Pluto, numerous forces attempting to stop such a thing from happening. Neil deGrasse Tyson is a well-known physicist and a significant contributor to the spread of an original point of view on our solar system's unsolved mysteries, particularly Pluto's intriguing case. Tyson, who is famous for his role in Pluto's reclassification as a dwarf planet, provides enlightening analysis on the ever-changing nature of celestial mechanics and the public's enduring fascination with unexplored space realms. Tyson's position regarding Pluto's reclassification is based on our expanding understanding of the solar system. He views the renaming not as a demotion but as a necessary adaptation to our growing knowledge of the numerous bodies that orbit the Sun. His approach to celestial mechanics is one of ongoing education and adaptation. He recognizes the complexities of orbits like Pluto's as evidence of how much remains undiscovered in space. The intrigue posed by these unknowns keeps space exploration exciting. Despite Tyson's confidence in his views on Pluto, a potential collision with Neptune presents a different perspective on his concerns regarding Pluto's orbital future. Could Pluto crash into Neptune, or is this speculation just another moment of confusion in the ever-changing landscape of space? Only time and further research will provide the answer. For now, we have gained a deeper appreciation of how much we still do not know about our own solar system. We continue studying these celestial phenomena in hopes of uncovering additional mysteries beyond. The possibility of a Pluto-Neptune collision raises yet another question about the unpredictability and fascination of the universe we inhabit. The idea that two celestial bodies with such dramatically different characteristics could collide is both intriguing and alarming, particularly given their current orbital stability. Pluto, located in the outer reaches of the solar system far from the major planets, is a frozen world, while Neptune, a massive gas giant, exerts a strong gravitational influence. Examining the ramifications of such a collision would provide profound insights into gravitational interactions and planetary evolution. To comprehend the dynamics of the solar system, one must first consider the composition and characteristics of both planets. Pluto, despite being a dwarf planet, contains a variety of frozen substances due to the extreme cold of the outer solar system. Its surface is covered in nitrogen ice, and its atmosphere consists primarily of methane, nitrogen, and carbon monoxide. Neptune, on the other hand, is a gigantic gas planet composed mainly of hydrogen, helium, and other lighter elements, with a substantial atmosphere. A collision between such disparate bodies would dramatically alter their structures and behaviors, possibly creating a spectacle observable from great distances. What makes this theoretical collision particularly fascinating is the influence of other planetary bodies in the solar system. Despite Neptune's gravitational pull playing a major role in stabilizing Pluto's orbit, it is not the only factor at work. The immense presence of Jupiter, a crucial element in the solar system, also exerts a stabilizing influence on Pluto's orbit, preventing it from straying too far into Neptune's domain. Additionally, Saturn's gravitational influence adds further complexity to the outer solar system's dynamics, making a catastrophic event between Pluto and Neptune even less likely. Recent studies suggest that Pluto and Neptune's interaction is not as straightforward as a simple collision course. Their gravitational resonance ensures that Pluto orbits the Sun twice for every 3 orbits completed by Neptune, creating a kind of celestial lock that prevents them from directly colliding. This resonance is one of the primary reasons their intersecting orbits have never resulted in an actual impact. The mechanics of these celestial bodies are finely tuned to minimize the risk of conflict. However, the long-term stability of Pluto's orbit remains uncertain. The solar system is constantly evolving, and subtle alterations in planetary positions or gravitational influences could disrupt this delicate balance. For example, if Neptune's position were to shift over millions or even billions of years, Pluto's orbit could become increasingly chaotic, potentially leading to a collision or even ejecting Pluto from the solar system entirely. Astronomers are also investigating whether other yet undiscovered objects in the outer solar system could influence Pluto's trajectory. Discoveries in the Kuiper Belt, where Pluto resides, have already expanded our understanding of this distant region. Other massive bodies within the belt could exert gravitational forces that subtly alter Pluto's path, making long-term predictions even more challenging. In addition to external gravitational influences, the Sun itself plays a crucial role in shaping planetary orbits. The Sun's gravitational pull is the dominant force governing the movement of all bodies in the solar system. Over time, changes in the Sun's energy output, such as the expansion of its outer layers as it nears the end of its lifespan, could significantly affect the orbits of distant objects like Pluto. Such changes might increase the likelihood of a Pluto-Neptune collision, a possibility that continues to be studied. As technology advances, astronomers can monitor these distant celestial bodies with greater precision, refining our understanding of their long-term movements. Despite the complexities involved, the probability of a Pluto-Neptune collision remains low in the foreseeable future. However, this scenario serves as a reminder of the unpredictable nature of the cosmos and the many mysteries yet to be uncovered. The concept of a Pluto-Neptune collision may be more of a speculative curiosity than an imminent threat, but it underscores the importance of continuous observation and deeper comprehension of the forces that shape our solar system. As we study celestial interactions, we not only gain a better understanding of the solar system's governing mechanisms but also develop a greater appreciation for the fragility and dynamism of the universe as a whole. The broader implications of celestial interactions. Beyond the specific case of Pluto and Neptune, studying potential planetary interactions provides deeper insights into the dynamic nature of our solar system. Planetary orbits are not static. They evolve over vast timescales due to gravitational perturbations, external influences, and even internal planetary changes. This understanding reinforces the need for continued research into orbital mechanics, especially in regions like the Kuiper Belt and the Oort cloud, where countless icy bodies move in complex and often unpredictable paths. The hypothetical collision between Pluto and Neptune serves as a thought experiment, challenging astronomers to refine models of planetary motion and gravitational influences. By simulating various orbital scenarios, scientists can better predict how minor changes in planetary positions might cascade into significant consequences over millions or billions of years. These studies also contribute to broader astrophysical questions about how planetary systems form, evolve, and sometimes even self-destruct. The role of external influences. Apart from planetary gravitational forces, other external factors could impact Pluto's future trajectory. For instance, rogue celestial objects, such as passing asteroids, comets, or even hypothetical interstellar objects, could exert minor but meaningful perturbations on Pluto's orbit. Such small nudges, compounded over millennia, could gradually shift Pluto into a more unstable path. Additionally, there is speculation about the existence of a large, undiscovered planet, often referred to as Planet 9, lurking in the outer solar system. If such a massive object exists, its gravitational pull could significantly influence the orbits of Pluto and other distant bodies, potentially altering their long-term stability. While Planet 9 remains hypothetical, ongoing observations and computational models continue to investigate its possible effects. The future of Pluto's status and exploration. While Pluto's classification as a dwarf planet remains a topic of debate, its scientific significance is undeniable. The 2015 New Horizons mission provided humanity with unprecedented close-up images and data, revealing Pluto's diverse landscape, active geology, and complex atmospheric processes. These discoveries reshaped our understanding of what a dwarf planet can be and reignited discussions about planetary definitions. Future missions to Pluto, or even beyond into the Kuiper Belt, could further uncover the mysteries of its orbit, composition, and potential interactions with Neptune. With advancements in space exploration technology, next-generation probes might one day return to Pluto, land on its surface, or even explore its largest moon, Charon, which has its own intriguing orbital relationship with Pluto. The unpredictability of the cosmos. Ultimately, the question of a Pluto-Neptune collision remains speculative. While current gravitational models suggest that their orbits are stable due to resonance, the ever-changing nature of our solar system means that absolute certainty is impossible over cosmic timescales. The study of celestial mechanics reminds us that space is not a static void but a constantly evolving, dynamic environment. Whether or not Pluto ever faces a collision with Neptune, its orbital dance with the gas giant continues to captivate astronomers. The mysteries of celestial motion serve as a reminder that our solar system, like the universe itself, is full of surprises, waiting to be discovered. Final thoughts. As humanity advances its knowledge of space, we must remain vigilant in observing and studying the intricate forces that govern planetary motion. While Pluto's future remains secure for the foreseeable future, the exploration of potential planetary interactions enhances our understanding of the solar system's delicate balance. Through continued research, we not only protect our understanding of celestial mechanics but also inspire future generations to look up at the sky with curiosity, wonder, and an eagerness to uncover the next great cosmic mystery.